Framing. Physical layer transmits bit stream to the destination over a channel. But, while transmitting, the signal may be corrupted with errors. To avoid this, the physical layer also adds some redundant bits to the signal. However, the bit stream received by the data link layer is not guaranteed to be error-free. So, it is up to the data link layer to detect and if necessary, correct errors. The usual approach for the data link layer is to break up the bit stream into discrete frames, and compute a checksum for each frame, and include the checksum in the frame, when it is transmitted. At the receiver side, it recalculates the checksum. If it matches with the checksum in the frame, then no error, otherwise, there are some errors. To break bit stream into frames, there are quite a few methods available. The first framing method uses a field in the header to specify the total number of bytes in the frame. When the data link layer at the receiver side sees the byte count in the header, it knows how many bytes are present in the frame, and hence where the end of the frame is. Let us take an example. Consider 3 small frames of sizes 4, 5 and 7 bytes respectively. The first number is the byte count of the frame. So we can say that the first frame contains 4 bytes, second, 5 bytes, and the third frame contains 7 bytes. It looks perfect, right? But still there is a problem with this algorithm. The byte count in the header may change due to the transmission errors. Suppose the byte count 5 in the second frame may become 7 due to a single bit flip, then the receiver will get out of synchronization. It is unable to locate the correct start of the next frame. Here comes the second framing method. It eliminates the problem of resynchronization of frames at the receiving node. It does this by adding special bytes at the start and end of each frame. That special byte is often called a flag byte. To separate one frame from the next frame, an 8-bit flag or 1-byte flag is added at the beginning and the end of a frame. This method was appropriate when only text data was exchanged by the data link layers. Here, the flag could be any character that is not used for text communication. Now, however, we also send other types of data, such as graphs, audio, and videos. Now the problem is, any pattern or character used for the flag could also be part of the data. If this happens, the receiver, when it comes across this pattern anywhere in the data, assumes it is the end of the frame. To solve this problem, a byte stuffing strategy was introduced. In byte stuffing, a special byte is added to the frame when there is a character in the data part with the same pattern as the flag. Whenever the receiver comes across the escape character, it removes ESC from the data section and treats the next character to the ESC as data, not a delimiting flag which tells the end of the frame. Byte stuffing by the ESC allows the presence of the flag in the data section of the frame, but it also creates some other problems. What happens if the original data contains one or more escape characters in the data section? The receiver removes the escape character, thinking that it is not the original data. To fix this problem, the escape characters that are part of the text must also be marked by another escape character. This is definitely a headache. Byte stuffing and destuffing. Well, the third method of framing gets around the problem of byte stuffing, which uses 8-bit bytes, just before the flag-like data. Why do we need to stuff 8 bits before the flag-like data, when we can do this, by just adding a single bit, to the flag-like pattern in data? So, framing can also be done at the bit level. In this method, each frame begins or ends with a special bit pattern, 01111110. This pattern is a flag byte. Whenever the sender's data link layer encounters 5 consecutive ones in the data stream, this layer automatically inserts a 0 bit into the outgoing bit stream. This is called bit stuffing. When the receiver sees 5 consecutive incoming 1 bits, followed by a 0 bit in the data, it automatically deletes the 0 bit.